So let's start off with a brief review of polar coordinates. You guys might remember that if you want to represent a point in the plane, I'm going to draw the XY axes here, even though we're not going to be using them really. But let's just try to find a relationship between polar coordinates and Cartesian coordinates. So if I have this point here, call it P, then in the XY plane, we describe this point by saying how far, let's call this X1, how far do we have to move in the X direction to get to the point? And then from there, how much further do we have to move in the Y direction? Call that Y1 to get to this point. And we write that the coordinates of this point are X1, Y1. And that ordered pair completely describes this point P. What we want to do now is notice that this, so in other words, before I continue, this point P lives on the opposite corner or on the diagonal of a rectangle in the Cartesian plane. And so sometimes these coordinates are called rectangular coordinates. What we want to do now is notice that this point also lives on a circle that's centered at the origin. Okay, a circle whose center is at the origin and whose radius is the length of this diagonal right here. This diagonal piece right here. So we can take a closer look at this segment right here and call the length of that R. That tells us how far away from the origin the point P is. And then we have to say where on the circle is this point, and so we can call that by this angle theta. We can describe that by this angle theta. And so this point P has what we call polar coordinates, r, theta. And of course we want a relationship between these two, these x and y and r and theta. And just by looking at this picture, we immediately think of trigonometry. And so these two coordinate systems are related by the two following equations, and that is that x is equal to r cosine of theta and y is equal to r sine of theta. And so these two sets of equations right here tell us how to get back the Cartesian coordinates if we're given the polar coordinates. Okay, and we'll talk later about how to go the other direction. But let's say now, well, we need to set some conventions, basically. There's one point in this polar plane that's different than all the others, and that's the origin here. So in the polar plane, the origin is called the pole. This point right here. So the origin is called the pole in the polar plane, and that's because at this point, we only need one piece of information to describe this point. This is the only point in the plane where the radius is 0. There's no circle with any positive radius that passes through that point and is centered at that point. Okay, so the pole is the only point with r equal to 0. All the other points in the plane, our convention is going to be that r is positive. Okay, and so r is going to be a positive number. And then to describe the point, remember in trigonometry, you can go around the circle many times and end up at the same point, but those two angles are very different, right? And so we're going to set our convention also that this angle, theta, should be between 0, less than or equal to 0, and then the angle is greater than or equal to 0, but less than 2 pi. Okay, and these are our conventions for polar coordinates. And as always, especially in this course, conventions are made to be broken. But these are the conventions. So we've got our polar equation right here. We're going to call this our polar transformation, together with some restrictions on what r and theta are supposed to be in order that we just get a one-to-one relationship between these two coordinate systems. Okay, we're in a chapter on integration right now, double integrals, and so obviously the whole point of this is that we're going to want to integrate functions over polar coordinate systems. And so to be able to do that, we need to understand what the area of a polar rectangle looks like. So first of all, we need to define this term. What the heck is a polar rectangle? And it's going to be maybe not exactly what you think, but kind of what you think. So it's going to be all the points in the plane. So a polar rectangle, let's just call it R, is going to be the set of all points in polar coordinates, r, theta, such that the r is bounded between two values, say r1 and r2, and the theta is bounded between two values, say theta 1 and theta 2. Now, if we were in rectangular coordinates, this would be truly a rectangle, okay? So we would write that this is like r1, r2 in interval notation, crossed with theta 1, theta 2. And again, this in rectangular coordinates truly looks like a rectangle. But what does it look like in polar coordinates? So it turns out that in polar coordinates, I'm just going to sketch this. Let's say theta equals a constant. This is a ray that emanates from the pole. We can call it the pole now, or the origin. So maybe this is theta 1, and this one over here is theta equals theta 2. These are just two angles here. The next question is, well, what about the radius? Well, we know what that is. So the radius says you can go out, say, to R1, and then go maybe a little bit further to R2. But you do this along every angle in the angles here, and what it traces out is like this little, what looks like a curved rectangle kind of. And so this is the shape right here that we want to try to compute the area of. So this is the idea. We want to find the area of what this is, a polar rectangle. Okay, and just by looking at this picture, this looks like it looks kind of like a slice of pizza, or what's called a sector of a circle that's had the tip of it bitten off or removed somehow. And so the way that we're going to compute the area of this magenta shaded area region here is to just compute the total area and remove the area of this yellow section down here. Okay? So to do that, we need to remember the area of a sector of a circle is 1/2 r squared times theta. Okay? Now, in this picture, the theta, the question about the theta, what should theta be? Theta is just the change in the angle from theta 1 to theta 2. So for us, we'll call that, say, delta theta. And just define that to be theta 2 minus theta 1. That's the change in the angle. That's how much this portion of this polar rectangle has actually opened up. All right, and before we compute this, we've got a couple more things we can define. The difference between R1 and R2, well, that we can just call delta R. So that's R2 minus R1. And we're going to end up, I know where we're headed here, so we're going to end up needing the midpoint of these two. And we'll call that R with a hat. R with a hat is the average of R2 plus R1 divided by 2. Okay? So this formula here is the area of any sector of a circle. We want to take the area of the larger sector and subtract off the smaller one. So the area that we're looking for, which I'll call delta A, is going to be the area of the larger one minus the area of the smaller one. So that's going to be 1/2 R2 squared times delta theta. That's the area of the longer R, longer radius. Take away 1/2 R1 squared delta theta. And both of these sectors have the same angle, so that delta theta can be factored out. And what we end up with is delta A, 1/2. The 1/2 and the delta theta can both be factored out, but I'm going to factor them out on opposite sides here. And so there's our difference, delta theta. And this is perfectly fine, but then we notice that this term here with the r's, this term right here, this one can be factored as a difference of squares. And so maybe we can get a more detailed formula here. And so we end up with delta A equals 1/2. And when we factor this as a difference of squares, it's R2 plus R1 times R2 minus R1, all times delta theta. All right, and now we just compare with these definitions that we've made over here. So this right here is our delta R, and all of this stuff in front is our R hat, or really we can just call this R moving forward. And so what we end up with is that the area of this little sector, this little polar rectangle, the delta A, this is going to be equal to R hat times delta R times delta theta. All right, and you can probably guess where this is headed because all of the integrals that we've been studying up to this point are integrals over small area elements, right? And so to finish off this video, let's just write down the effect that changing to polar coordinates has on our integral, and it's all going to be coming from this R right here. All right, so let's suppose that we want to take a double integral over some region D of a function of xy, okay, in the usual xy plane. But let's say that we know how to represent D in polar coordinates. It's kind of nicer or easier for us to think about that in polar coordinates. Well, we can plug in our x equals r cosine of theta and our y equals r sine of theta into our function, and this will force our function to become a function of r and theta. Okay? The next question is, well, if we're going to integrate with respect to r and theta, then our dA has to be in terms of r and theta. And we just found out that a small polar rectangle has the area r delta theta. This r had a hat over it, but remember, in an integral you take the limit, and so that average of the 2 points will just approach r itself. And so this tells us that our dA is going to become r dr d theta. We're going to always have to multiply our integrals by r when we switch to polar coordinates. Okay, and so back up here we can write down our integral. Polar coordinates don't change the shape of the domain, so the domain is still just d. That part hasn't changed, but our function is now a function of r and theta, and our area element becomes r dr d theta. And so if we want to integrate in polar coordinates, the key thing to take away from this is don't forget this extra r right here.